Este investigador se llama William DeDoncker, se mudó de Chipre a Londres, donde hace investigación, y se mudó allá en el 2011. Hizo un grado en biomedicina, luego hizo un máster en neurociencia clínica y empezó a trabajar en el Instituto de Neurología en la University College London, y específicamente en el grupo de trabajo y de investigación que se llama Effort Lab. Ahora mismo está haciendo su doctorando y se dedica a investigar la fatiga crónica. La fatiga crónica es un síndrome en que básicamente, como el nombre define, la persona está muy fatigada. No hay una razón médica específica y conocida ciertamente hasta el momento, pero se da en algún momento de nuestra vida en muchas personas y a lo largo de la población. Y básicamente se define como sentirse muy cansado y aunque por mucho que uno descanse, esa sensación no desaparece. Pero bueno, tras esta breve introducción, presentaros simplemente sin más dilación a William DeDoncker, que pasa ahora ya en inglés a explicarnos un poco de lo que está investigando. William, thank you very much for explaining to us and sharing your time with us.
Oh, thank you very much, Alex, for the invitation. So, hola a todos. This is not very different to what I was expecting initially. I was expecting an e-seminar, but with maybe a bigger audience than just Dr. Alejandro. So we will make it this way. We will make it happen. Well, hopefully everyone is okay and healthy. So I will give you now sort of a simplified version of my work that I'm doing as part of my PhD, but also as part of my position as a research assistant on this project in the Effort Lab at UCL, trying to understand a little bit more about what causes chronic pathological fatigue. And sort of the hypothesis we're testing is that fatigue arises because of an altered effort perception. So I will give you some insight into this. But firstly, let's start off by explaining what is fatigue. So fatigue is something that is common to everyone, whether it be soldiers in World War I, whether it be miners, elite athletes, or even now these days, doctors and nurses fighting this deadly COVID-19 virus. And what's interesting is that the study of fatigue was stimulated initially by the Industrial Revolution. So no one really studied fatigue prior to that. And Angelo Mosso here, which was one of the pioneers to study fatigue, and wrote a fantastic book called La Fatica in 1891, sort of came up with a nice description of what fatigue is and sort of divided it into two sections. The first part of fatigue is that it is a diminution of muscular force. And the second is that fatigue is a sensation. So what most people, even in these examples, show is that fatigue is perceived. It's a sensation that you perceive. And he's very clearly stated that we begin to perceive it being fatigue, only when it has attained a certain intensity. So this was a nice definition of fatigue in 1891. And to be honest, the definition of fatigue now in 2020 hasn't really changed much. We don't really know much more about fatigue than what we did then. But what's interesting is that the Industrial Revolution led to the study of fatigue in World War I soldiers and in workers to try to understand why are people getting tired, how can we make people work longer, sort of how we can make soldiers to push through for longer. And this sort of led to the development of exercise physiology and to study human performance and in athletes. So this is what we know as fatigue and what all of us experience as part of an evolutionary trait. And we tend to call this what we call physiological fatigue. So here I'm giving an example of physiological fatigue from an exercise perspective. But this is not to say that it is different from cognitive fatigue. So a lot of people try to distinguish between exercise-induced fatigue and cognitive fatigue. But to be honest, fatigue is the final output. Fatigue is a final sensation, irrespective of what the trigger is. But what is very common about exercise-induced fatigue and what they call cognitive fatigue is that it is usually induced by repetition. So doing many repetitions will bring on fatigue. It can be delayed. So if you're doing from an exercise perspective, if you do the right form of training, the onset of fatigue can be delayed. It is influenced by reward, so that if you're sort of training to be an Olympian and to win an Olympic gold medal, that reward of the medal will sort of allow you to push through the fatigue. And it is alleviated by rest. So rest, if you rest, then your fatigue goes away, and then you can come back the next day or whenever it is. And from an exercise physiology perspective, there's been a number of different definitions that have tried to work on that initial definition by Angelo Mosso in 1891. And one of them by Edwards was that fatigue is a failure to maintain the required or expected force. So this was then very quickly afterwards revised to sort of a definition, what I call version 2, in that it is an acute impairment of performance that includes both an increase in the perceived effort. So this goes back to what Angelo Mosso said about being a sensation. So the sensation is the perception of effort, which is necessary to exert a desired force and an eventual inability to produce this force. So this is what we all experience or have experienced at some point in our lives. But then again, this is by no means a definitive definition, and that's why I have here definition version ... We're still working to come up with a more accurate definition of what fatigue is. But fatigue is not only from a physiological perspective, fatigue also exists in pathological state. So in a number of neurological disorders, and here I've set out 3 examples just to name a few. So this is in stroke, in multiple sclerosis, in Parkinson's disease. Fatigue is a prominent symptom in all of these diseases, but we don't really understand how it arises. So what is different in pathological fatigue to physiological fatigue is that it is not induced by repetition, so it can appear just like that. It cannot be delayed, so once it comes, and no matter what you do, you can't really prevent the symptom of fatigue. Reward, I've scratched it out, but reward can influence the onset of fatigue and delay it slightly, but not in all cases. So this is very rare. So it can't really be manipulated by reward. And rest doesn't really do much to help with the symptom of fatigue. So even if you rest a little bit, you can still wake up the next day and still feel tired. So this is sort of quite important to understand. Why does fatigue arise in this pathological state? Because as you can imagine, it has a severe impact on the quality of life of these patients suffering from these neurological diseases. So what we're interested in part of our lab is, how does fatigue arise? What are the mechanisms driving it? So if you understand the underlying neurological mechanisms as to what drives and mediates fatigue, then we can sort of answer the final question, and a key question it is how can we reverse it? Can we reverse fatigue? So just to give you an outline from a patient's perspective, what it's like to live with fatigue, so there was this very nice description from the Multiple Sclerosis Trust in the UK, which says, this is one MS patient describing their fatigue, saying that fatigue feels like being weighed down, as if you're trying to walk up to your neck in a deep, muddy river in heavy, wet clothes, carrying shopping bags full of rocks. So even if you've never done that, and I doubt that anyone has gone and done that himself, but you can imagine that it can be quite difficult. The other definitions, so these are definitions from some stroke patients that we have seen at some of our experiments, and we asked them, can you describe what fatigue is for you? And one of them came up that, being an invisible problem, I worry that no one believes me or can do anything to help. So this clearly states that fatigue is a problem, but because you can't really see it from the outside, it's not really diagnosed. It's not something that people tend to study too much. And that I suffer extreme fatigue, which follows no pattern whether I rest, exercise, or perform daily tasks. And then again, this goes in line with what I described previously, in that it can't be alleviated by rest. You can always feel fatigued, and it doesn't really matter what you do. It just appears just like that. So if we go back to that last definition, definition version 2, as we called it, as to what is fatigue, it's an acute impairment of performance that includes both an increase in the perceived effort necessary to produce a desired force and eventually an ability to produce this force. But from these patients' perspective, physically, they are still fine. So they are able to produce this force, but yet their perception of effort, if you look from these definitions, seems to be altered. So this is what we're trying to focus on in our lab, trying to focus on what is perceived effort and how might that change in disease state. So what is perceived effort? So perceived effort, to put it in simple terms, from a physical perspective, it is the experience of a muscle contraction, right? So when you feel tired, just moving feels like you can actually feel the contraction itself. But what mediates this experience, right? So what controls this experience? Is it the expectations from the brain to your body? Or is it the sensory input from the periphery to going to the brain that sort of drives this perception? And to be honest, there is evidence for both. So there's no clear-cut answer as to whether it's from the brain to the periphery or from the periphery to the brain. But it seems to be a combination of both. So if you look at the top-down influences, so these are the influence from the brain to the periphery, there's a number of different studies which show that the perception of effort, so PE here is perceived effort, it increases it correlates with pre-movement, movement-related cortical potential. So this is a potential recorded before movement onset via EEG. And the lower the movement-related cortical potential, the higher the perceived effort. And it also correlates during the task performance. So not only before the movement itself, but also during the movement. Studies using non-invasive brain stimulation have shown that a low-frequency stimulation over the primary motor cortex during task performance increases the perception of effort. And also, if you disrupt the sensory motor area, the supplementary motor area, but not the motor cortex, it also reduces perceived effort. So there is some link there between sort of central brain mechanisms which mediate the perception of effort. But there is also evidence from the periphery. So the sense of effort is disrupted during muscular paralysis or in sensory neuropathies. So if you block the muscle, the input from the muscle to the central nervous system, there is no sense of effort. The centrally generated signal must interact with the afferent input to generate awareness. So you're only aware of the contraction when there's an interaction between the motor output and the afferent input. The sense of effort is altered by altering proprioceptive input. So if you sort of modify, give the sort of an illusion studies, ask them to move their hand and ask them where they perceive their hand to be and where it actually is, the sense of force seems to be altered. And your visual expectations also tend to influence perceived effort. So from this, we can see that perceived effort is definitely not something simple. It's something quite complex, but seems to be mediated by both expectations of your sensory input and the actual input you're getting. So how can we then try to explain perceived effort within sort of a framework which might allow us to explain pathological fatigue? And this is where our lab, so Dr. Anna Kupaswamy, has come up with sort of this theoretical model using the active inference framework of sensory motor control to try to explain perceived effort and fatigue. So the nice thing about active inference is that it combines both top-down, so from the central nervous system to the periphery, and bottom-up, from the periphery to the central nervous system. It combines the two processes dynamically. So therefore, we can use the evidence from the prior perceived effort studies and try to integrate them to form a single model of perceived effort. So I'm going to try to spend some time to explain this framework because it can actually be quite complex. So what this says is that the central nervous system operates by predicting the sensory input of the upcoming movement, right? So it operates by sending predictions rather than sending out the motor output. Then the predicted sensory input is compared to the current sensory input you're getting at this moment in time. So, and the mismatch being the difference between the prediction, the predicted sensory state, and the actual sensory state is used to generate a prediction error. And the aim of the system is to minimize this prediction error. So you want to have as low a prediction error as possible. And in order to achieve this, it can do it in two ways. It can either do this by changing the predictions to match the current sensory state. So, and that's what we call perception. That's when you're perceiving something. Or you can change the prediction error through action, so by acting. So therefore you can act to fulfill your prediction. So to change your current sensory state to match your predicted sensory state. And when acting on the world, the precision of the ascending prediction error, that being the error that goes back up to the central nervous system, or what we call sensory precision, is reduced, because in a way you're fulfilling your predictions, right? So if you intend to fulfill your predictions, then you have to change your motor output to change your current sensory state. And therefore your precision here, your sensory precision, is reduced because your predictions were accurate. And within the cortex, the process of changing the precision of prediction error, it can be thought of as attention, right? So attention, or a more commonly used term, is sensory attenuation. And you can think of attenuation as being the inverse of attention. So sensory attenuation is your ability to attend away from sensory input that's predictable. And you can think about it as that when the sensory precision is low, sensory attenuation is high, which explains why the perceived intensity of self-generated actions is low. So if I'm moving like I'm moving now, I'm moving my hands while I'm talking, they are self-generated actions, but I don't perceive them to be effortful. So they're automatic, it's automatic behavior, because it's something that's predictable in a way, right? So my precision is set to low. I'm attending away from the sensory input, which is going back up to the central nervous system, because my actions are predictable. And therefore they feel effortless, or the perception of effort is low. But by increasing the sensory precision, so if you increase this precision, then the perceived intensity of the self-generated sensations also increases, right? So if you're increasing the precision, your sensory attenuation goes low. So therefore you're not attending away from the sensory input. So therefore there's more processing of the sensory input. And therefore that's why you get the feeling of high effort perception. And you can think of it as, if there is abnormalities in this modulation of precision, it can therefore lead to a false inference about what is going on. So, and if the sensory precision is always set to high, so if you're not able to modulate this and you're always at this end, you cannot attend away from the sensory consequences of self-made actions. And then they're always perceived with a higher intensity than usual, and therefore are perceived as more effortful. And this is what we're suggesting is the case in fatigue. So they're not able to modulate the precision. So they're not able to attend away from the sensory input of their self-generated actions. And that's a result of poor sensory attenuation. So poor sensory attenuation gives rise to abnormal perception of effort. And you can think of it as that if you're constantly perceiving every action you do as more effortful, then that will give rise to the feeling of fatigue. So prolonged experience of high effort gives rise to the sensation of fatigue. So it's quite a complex sort of model to try to understand, but to put it in the most simple terms is that if you're not able to pay less attention to the input you're getting as a result of your actions, then it's going to feel more tiring, right? So that has to do with the perception of effort. So this is sort of a model in which we're trying to explain perceived effort and therefore fatigue. But in order to study this, we somehow need to sort of think of a pathological model of fatigue, which we can test this hypothesis in. And as I described previously, it's present in a number of neurological disorders, whether it be multiple sclerosis, Parkinson's disease, or stroke. And in our lab, we are actually focusing most of our work on stroke survivors. And the reason being we focus it on stroke patients is that once you've had a stroke, it's a one-off event. It's not a progressive disorder. So you have an area in the brain dies, so it's no longer living tissue. Surrounding areas can take over its function, but the disease does not get worse over time. So therefore, the symptom of fatigue, then we wouldn't expect it to change much as disease progresses because it doesn't tend to progress. Whereas in other diseases like multiple sclerosis or Parkinson's disease, that we know that the disease gets worse over time. Therefore, we don't know whether changes in fatigue in those diseases, whether it's as a result of the disease getting worse or it's just fatigue changing. So we thought of that stroke might be a nice model to study it in, but it doesn't necessarily mean that any of our findings are restricted to stroke. They can apply to these other disease states. So fatigue in stroke survivors is not surprisingly known as post-stroke fatigue. What do we know about it so far? It has a severe overlap with other affective symptoms. So affective symptoms are symptoms that the patients describe. It's very hard to see them from an outsider's perspective. And every 10 people that have a stroke, 8 of them seem to suffer from fatigue. Of course, these numbers will vary across different countries and depending on which papers you read, but on average, it approximately seems to be about approximately 80%, of which 7 of these will also suffer from depression, so 7 of the 10. 5 of the 10 will also suffer from chronic pain, and also 5 of these also suffer from sleep disturbances. So you can see that fatigue in itself has a very high overlap with a lot of other symptoms, and that's why it's actually very difficult to study fatigue alone. And that's one of the reasons why fatigue hasn't really been studied in these neurological states, especially in stroke, for many years, because it was considered to be a secondary symptom to these other symptoms you have here, such as depression. So people were told, well, you're depressed, that's why you're fatigued. So let's treat the depression and the fatigue will go away. Whereas we know very clearly that that's not the case. Fatigue can exist independently of other affective symptoms. And what's interesting is that in people that have a stroke here, so this is an example of a stroke. So I'm not really sure if you know, most of you know what a stroke is, but it's it can either be a bleed, so a blood vessel in the brain bursts, or a clot in one of the blood vessels, and therefore the blood doesn't reach the areas upstream of the damaged blood vessel, and that region of the brain is now for dead tissue, as it no longer has a blood supply. And what we also know is that in post-stroke fatigue, it doesn't really matter where in the brain the stroke was, so it's irrespective of the lesion location. It doesn't really matter what type of stroke it was, whether it was a hemorrhagic stroke or an ischemic stroke. It doesn't differentiate across genders, so it's equally prominent in both males and females. Age doesn't really matter, even though if you read some papers, it seems to report a higher incidence amongst younger stroke survivors. And actually that's not surprising, because if you have a young stroke survivor and they're recovered quite well, but their only symptom is fatigue, they are expected to go back to work. So therefore, because they're trying to push themselves slightly more to go back to their normal life, it is possible that that's one of the reasons why there's a slightly higher report in younger age groups. And there is no obvious trigger. So there is a sort of a review we wrote with Anna a couple of years ago, which sort of gives you a nice outline of the basic demographics surrounding post-stroke fatigue. So what we get from this is that it is quite complex, and we need to sort of be very careful when trying to test these different hypotheses as to how we can make valid conclusions that are specific to fatigue and none of these other symptoms. So what are the origins of post-stroke fatigue? So we know that early on following a stroke, there is an exposure to cytokines, and that leads to inflammation within the brain. And that's probably why in the acute phase, so acute being in the first week, in the first month following a stroke, the majority or almost all of the stroke survivors report fatigue. And there is evidence to suggest that that's a result of the inflammation itself. But once the inflammation goes up, then we expected once the inflammation goes away, we expect that the fatigue would go away, but it doesn't in some cases. So it's very possible that this early exposure to inflammation results to alterations in cortical neurophysiology and behavior. So this is where I'll show you some evidence in the next couple of slides, and this is where we primarily work on, which results in a non-reversal of cortical neurophysiology, and in the long term gives rise to the symptom of fatigue, right? So you have inflammation, which results in changes within the brain, and in terms of behavior, which gives rise to the symptom of fatigue. And this is where we're focusing on. So our lab, we mainly try to understand what are these alterations and how can we identify through this, what are the mechanisms that result in the symptom of fatigue. And one of the ways we do this is by studying neurophysiology. So neurophysiology, we can study it using what we call transcranial magnetic stimulation, which is a form of non-invasive brain stimulation. What we do with this is you have a magnetic coil, otherwise known as a TMS coil, shown here. And if you place it over the motor cortex, so the area of the brain which controls movement, and you give a brief magnetic stimulus, that magnetic stimulus will penetrate the skull and induce an electric stimulus at the surface of the brain, okay? And it can stimulate sort of the cortical spinal tract directly, or it can stimulate a number of different inputs to that area of the brain. And what it does, it produces a muscle activity on the contralateral side. So if you think of the area of the brain, so the motor cortex, and if you think of the area which controls the hand muscles, so the left side of your brain controls the right side of your body. If you stimulate the area which controls the hand muscle on the left side, what we do is you get involuntary movements in your right hand. And what we can do then is to quantify this and measure actually what is the size of the response by looking at the motor evoked potential, right? So therefore we can see the activity between the brain and the muscle response. And using this technique, using magnetic stimulation, our lab sort of published a study, which was one of the sort of leading studies which sort of pushed this work in 2015, which showed that when in people with varying severity of fatigue, so fatigue is plotted here on the x-axis using the fatigue severity scale. So 1 indicates no fatigue, 7 indicates very severe fatigue, and this was all in stroke patients, which were chronic. So they were at least 3 months after their stroke. They were not depressed, and they were physically well recovered. So in most of our work we do in our lab, in order to sort of restrict any findings we have to fatigue itself, we only recruit very specific stroke survivors to our study, which don't have any physical impairment, are not clinically depressed, haven't had multiple strokes, and therefore we're sort of controlling for the wide range of other symptoms that are present with fatigue by sort of having a controlled group of patients. And what we saw here is that with higher severity of fatigue, the higher was the resting motor threshold. And what resting motor threshold is the intensity of stimulation required using this technique, using transcranial magnetic stimulation, to get the same response in the muscle. So you want to get a response of the same size in everyone. And what you're doing is you're measuring what output of the machine do you need to get that same response. And those with higher fatigue, you can see here, those with a 6 or 7 had higher thresholds. And you can see that the responses are quite variable, and they are variable to everyone in the general population. So you can get people, even healthy people, with high thresholds or low thresholds. But what's interesting is that there are no high fatigue patients, so those with 5, 6, or 7, for example, that had a low threshold. All of them had a high one. So therefore, we have an idea that there is some difference between the excitability of the brain or the motor cortex that relates to fatigue itself. So therefore, that leads us on to how does neurophysiology, which we sort of talked about now, how does that relate to actual behavior? Is there some relationship between the two? And this was a study which was done in a group of healthy people, which showed that if you artificially change the excitability of the brain, so this was all done in healthies, so what they try to do is to bring everyone down to here, basically. They try to reduce the excitability, meaning that you needed a higher intensity to get the same response. And you can do that using a number of techniques, which is not important for now. And therefore, that changed how they performed what we call a force matching task. So a force matching task is people are given a force to their finger, and then they're asked to match it by pushing against their own finger. And what you tend to see in this task is that people tend to apply more force than what they felt. And the reason for that is because of sensory attenuation. So sensory attenuation, just to summarize again, it's your ability to attend away from sensory input that's predictable. So if you're going to self-generate a movement, you can predict the sensory input you're going to feel, and therefore you modulate attention away from it, right? So therefore, if you want to match it, you tend to push a bit more. Whereas if you have to do the same thing with a robotic device or with a joystick, then you tend to be quite accurate. And this is what we see here. So people, when they have to match using the joystick, they're quite accurate at matching what they felt. So if they felt a 1 Newton force, they tend to apply close to a 1 Newton force. Whereas if they have to do it themselves, when they feel a 1 Newton force, they tend to apply a 2 Newton force. So people tend to overshoot. And sort of how some people tend to describe it is why some children, when they're fighting at the back of a car, they always tend to say, he hit me harder, no, he hit me harder. Well, they actually are hitting each other harder because they're attending away from the sensory input that they're giving. So this is a way which actually links the excitability of the brain with behavior. So given that we saw low excitability in the brain, we wanted to ask the question, is sensory attenuation affected in these stroke survivors? So given that patients with high fatigue needed a higher intensity of stimulation to get the same response, or it means they have lower excitability, will they be more accurate in matching than those with low fatigue? And this is one of the studies which I have done as part of my PhD, and the analysis is ongoing. But what they did is people applied a force to their finger. This was a target force. They felt it for 3 seconds. They were given a cue to do nothing and wait for 3 seconds. And after that, they were given a green cross. So it's a go cue. And they were asked to match the force they just felt by moving the device themselves and pushing against their finger. And what we're interested in seeing in this study is that what is the difference between the matched force and the target force, right? So that gives you a measure of how accurate they were at matching. And what we expect to see is that those with high fatigue will be better at matching because of their sensory attenuation being reduced. So what we said before, high sensory attenuation means low effort, low sensory attenuation means high effort. So that sort of might give us a link between sensory attenuation and effort that people perceive. So this is one of the tasks that I'm doing, and hopefully the results will come out fairly soon. We're still trying to analyze the results. But another interesting study which sort of was done and has led on to some work which we've currently finished, and I will share that with you very shortly, is regarding altered perception and behavior. So one very common symptom following a stroke in a number of stroke survivors is the perception of limb heaviness, meaning that they feel their arm to be heavier than what it is. It doesn't seem to be related to motor weakness. So it's present in stroke survivors which are physically very well recovered, but it does seem to be related to fatigue. So what we have here is a plot, the fatigue score, the same as described before. 1, no fatigue, 7, very severe fatigue. And these are people that disagreed with the statement, my limbs can become very heavy, and people that agreed with the statement, my limbs can become very heavy. And you can see that more people with high fatigue agreed with the statement than they disagreed with the statement. And if you look at their motor impairment, so how physically recovered they were, they tend to be pretty matched up, right? So it doesn't be this, again, this provides evidence to suggest that it's not related to weakness. And what is limb heaviness? So it could be, again, related to sensory attenuation. If you're not able to attend away from the sensory input that you're getting from your muscles, then it constantly is being perceived as heavier, right? And if you have everything is constantly perceived as heavier, you can think of it in a way that is perceived more effortful. And so that's a nice, interesting perceptual study. And if you look at their behavior, so these are a number of different measures, which I'm not going to really go into much, but if I just show you this one here, this shows movement speeds. So how quickly people move, right? So they're asked to move from point A to point B as quickly as possible. And what you tend to find is that those with high fatigue, so here the high fatigue ones, tend to be slightly slower when compared to the low fatigue groups. Whereas in all other tasks, whether it be a reaction time task or a choice tasks, they're not different. So, and it's only specific to their affected hand, not in their unaffected hand. So again, this is another sort of behavioral result, which allows us to sort of build on this model of sensory attenuation. So from this perceptual experiment, this limb heaviness, we went to study perceived effort directly, right? So this is sort of the last set of studies that I'm going to talk about. And what we did here is we wanted to measure perceived effort and behavior. And what we did, we got stroke patients with varying severity of fatigue again to perform a grip task. What they had to do is they had to squeeze at different percentages of their maximum voluntary force. After they had to squeeze, we wanted to sort of measure the perception of effort without asking them directly. So we didn't want to influence their report bias in how they perceive stuff to be effortful. And we showed them lines of different lengths. So just to simplify this, imagine you had to walk from Madrid to Barcelona. That's a long distance, okay? But you had to walk that distance with a 10-kilogram backpack. It's quite heavy, but not too heavy. You would say that it is tiring. But imagine you had to walk the same distance, but this time, instead of a 10-kilogram backpack, you were given a 50-kilogram backpack. You would actually say that it was a lot more tiring, even though the distance was the same, right? So how much effort you had to exert to cover the distance influenced sort of your report bias. And this is what we try to achieve with these tasks. So we showed people the lines of different lengths. We gave them instructions as to what is a short line and what is a long line. And what we asked them to do is, following different squeezes, we asked them to tell us, based on the lines they saw previously, is this short or is this long, right? And what we expected to see is that after a harder squeeze, so a squeeze at, let's say, 60% of their maximum, what was previously described as short would be described as long. So their report will change based on how much effort they had to exert directly previously. And then we also asked them to rate their confidence. So how confident are you in your response? So this gave us what we call an implicit measure of perceived effort. And then we also had an explicit measure where we asked them to squeeze again at the same forces, but this time we just asked them the question, how hard was it? And they had to report on a scale of not at all to very hard as to how hard they thought the squeeze was. And during this task, we could measure their behavior. So let's say this is a force trace. So this is what we get after every time they squeeze. This time the target was 40%, so 0.4, so 40% of their maximum. And it gives us what we call target overshoot. So how much above the target did they squeeze to? How long did they hold the squeeze for? And just by looking at the force trace, we can see as to how variable was the force they were exerting, how variable was the output. And what we saw from this study is, if we look at this implicit effort, so on the y-axis, what we have is the number of lines reported as long, okay? And on the x-axis, what we have is their fatigue scores. Again, the same scale as before. 1 is no fatigue, 7 is very severe fatigue. And what we see is that with increasing fatigue, there is more lines being reported as long. And this is in the 20% effort condition, this is in the 40% effort condition, and this is the 60% effort condition. So this is primarily, it's present across all three conditions, but is significantly present in the lower effort conditions, but that they're perceiving the task to be more effortful, even at low force conditions. And if we look at the explicit effort, so the explicit is when we ask them directly, how hard was it? We only see a relationship at the 20% condition, right? So with increasing fatigue, they're actually reporting the effort to be higher. And this is actually quite nice. So if we look at sort of highlight these three results, so there's a higher implicit effort with those with high fatigue, and there's higher explicit effort in those with high fatigue, but only at the low effort condition. And actually this fits very nicely with what patients that suffer from fatigue report, is that it's only the simple activities of daily living which feel more effortful than they did before. And if you think of what are simple activities of daily living, they are making a cup of tea, having a shower, brushing your teeth. These are usually low effort tasks. And it's those tasks that these patients that suffer from fatigue actually describe to be harder than they were previously. They are still able to do the higher effort tasks, and they perceive it to be just as difficult as those without fatigue, but it's those low effort tasks which feel more tiring. And what we see here is actually, this is another way of describing the implicit result, is you have the line length, so the length of the line they described. So the 6 centimeters was the middle. And what we see is that the red line is those with high fatigue, the black line is those with low fatigue. So you can see that the curve shifts more to the left. So therefore, those with high fatigue are perceiving a 5 centimeter line, for example, if you look at here. So here, there is 40% of participants are perceiving a 5 centimeter line to be long, whereas here, they're perceiving it, a smaller percentage are perceiving it to be as long, right? Or the line is slightly longer. And what we also see in their behavior is that they have a higher target overshoot, and the duration of the hold is different. So there's also some behavioral measures which are different across these patients, which might give us understanding of how fatigue arises. So to summarize, it's been I think I put maybe too much information in this, but if you have any questions, I'm happy to answer them, any of them via email. But there is a higher perceived effort in post-stroke fatigue, just on this study we showed you just now. The perceived effort arises from sensory attenuation. Again, sensory attenuation being your ability to attend away from predictable sensory input. Diminished sensory attenuation gives rise to high perceived effort. So if you're not able to modulate your sensory attenuation, everything is feeling as more effortful. And it could be that post-stroke fatigue is a result of diminished sensory attenuation. And hopefully we can answer this question using that force matching task I described earlier. And as part of our lab, we're sort of doing a number of different other tasks to try to answer this question. So we're doing some TMS tasks, some EEG with across different sensory domains, whether it be with hearing, with vision. And we've also finished a neuromodulation task where we try to change excitability. So you can actually artificially increase excitability. So in those patients we saw before that had low excitability, what happens if we bring that back up? Will that change their fatigue? And actually from our results, we see that it does. So we're trying to understand what are the mechanisms behind it. And hopefully I can share that with you at some other e-seminar that Alejandro will organize at some point, maybe again in the near future. So these are a number of different tasks that are either done or are being done or we plan to do in the near future. And on that note, I want to say gracias. And I want to thank firstly my supervisor, Anna Kupuswamy, we're climbing a big hill to work towards understanding fatigue when we still have a long way to go. But she seems a bit more tired than I am already. And these are all the people that have contributed in some ways. This is my email. If you have any questions, I'm happy to answer them via email. Or if you want me to send you some material, it's perfectly fine. And of course, the people that support our work, which is the Wellcome Trust.